Okay, so I'm a bit of an outsider at this meeting in that I work in formal methods, particularly with proof of systems, but not in security. So there won't be anything fancy related to security here, but it will be rather an introduction to proof of systems or to interactive theorem provers, and with a simple example of protocol verifications, just so if you haven't seen such a thing before, so that you may get a feel of how it is to work with this kind of systems. Okay, so I'm sure a lot of people know this, but let's say that interactive theorem provers are softwares in which you can write mathematical statements, in principle, anything you can imagine, and then you write proofs for those statements, and the system will check for their correctness. And this happens interactively, so you don't just write the proof and check it, but rather have a actually huge proof. You do some small step that you think will advance the proof, then the system will give you the feedback of how the thing you need to prove from this point on has changed, and so on until you are left with nothing to prove, and thus concluding the proof. To mention some systems, there are Amda, Koch, Isabel, Lin. We will focus on Lin in this talk. Also other systems, for example, F-star has been mentioned here. F-star is a bit of a different flavor than the systems, I would say. And yeah, one aspect is always with this kind of systems that verify correctness is a question that you can't really escape fully, is that when the software said that the proof and your statement is correct, is true, but why would you trust the system? Because maybe the system is buggy and allows you to prove false things. So the answer in general here is that they are they isolate the trusted code base. And here by this I mean the part that guarantees the soundness of the system. So the part that's relevant for you not being able to derive false statements. Is usually a small part of these huge systems. For example, for Lean, people have written independent third-party verifiers of thousands of lines of code as a magnitude, which is pretty small in this context. Okay, so we will focus on Lean. As I said, it is an example of a proof of system. It is, as of now, also a fully fledged functional programming language. So in that sense, we can think of it as competing with both something like Coq and with something like Haskell. A nice thing about it is that it has a very rich metaprogramming framework, which I think could be potentially useful in our context in the future, in that it is a system that it is well suited for building DSLs and maybe some proof infrastructure more specialized in security and cryptography. And also it gained traction recently, mainly because of its huge library of formalized mathematics called Mathwib, and also some other remarkable high-level mathematics formalization projects. And insofar, the mathematical applications sort of outweigh the computer science-related applications in Lean. That's not to say that they do not exist. For example, there is the CEDAR project that was mentioned here yesterday. I think also the Iris Lean project, which is a port of the Iris project from Coq to Lean, and so on. So now we'll go through an example, and that will be it. We'll focus on proving the semantic security of the LGML protocol as a toy example. We won't go into much detail, just to mention some different implementations and frameworks related to this. I think the first formalization was one by David Novak in COG, and later several frameworks have been built in COG, like the foundational cryptography framework, EasyCrypt, also SS Proof, on which I think we will have a talk later today. There is also libraries for AMDA, which verifies different protocols, libraries for Isabel. And for Lin, there is this cryptolib library, which was made in the master thesis of Joey Lupo at the University of Edinburgh. And we will look a bit at this library in the following. So I want to emphasize that what I present is not some original work of mine here. It's just examples from cryptolib, which is written in Lin 3, and as George mentioned yesterday, Lin was a big change from version 3 to version 4, which is not backward compatible at all. So a lot of projects remain in Lin 3, although the standard library was fully ported to Lin 4. So I've been working a bit on translating cryptolib from Lin 3 to Lin 4, but all credits here is to Joey Lupo, the original author. So what is proved using this library is based on the notion of a semantic security game, where a challenger, this is a formulation for public key protocols, challenger picks at random a public key, and an attacker potentially using that produces two messages, and one and two, and then the challenger encrypts one of them at random, and then the task of the attacker is to determine which one was proved. And then we say that A wins the game if it essentially cannot do better than coin flipping up to a negligible number. Okay, now we'll look at some code that's look a bit intimidating at first, but the point is that the pen and paper description can be formalized somewhat resembling the previous description. So here, one very useful thing is that we may use this very large library of formalized mathematics, for example, to make formal use of notions of picking at random and all these sorts of things, which take a bit effort to make formal. So in Lin there is this variable statement, which essentially says, let these things be of this type, as you would write on pen and paper. So you essentially declare some arguments for future functions. So you assume some types for the public key. The key is the message, the cipher space, and then we assume we have a random key generation procedure here. So this PMF is a probability distribution. It stands for probability mass function here. So we can pick at random something using this. We can assume that we have some unspecified encryption and decryption functions. Then we have an attacker here, which is a function whose type resembles the pen and paper description. And so it takes the public key and produces two messages. And this is the first step, and then it takes a cipher and outputs a random bit. So 0 or 1 with the probability distribution. And then we can find this, which I think is a quite convenient way of describing it, based on a very nice observation. classical, very nice observation that probability distributions form a monad. So we can do this very nice syntax. So we can just generate some keys the attacker produces, the messages. We choose 0 or 1 arbitrarily, and then we encrypt one of these messages, and then the attacker produces a bit based on the guessing in this way, which one of the messages was encrypted. And then we can specify the main property by essentially defining the probability for the attacker to output 1 here, this P variable here, and then we ask for this probability to be within a negligible bounds from 1/2. And this is a proposition which is part of the lean type system, so it is something that later we will need to prove about a specific instantiation of the previous function, which does specify a protocol, and we also may as well specify the correctness of the protocol in that decryption and encryption are inverse to one another. Okay, and as I said, as a toy example, we will use the LDMR protocol, and to express it in its generality, we again make use of the mathematical library that exists within Lean. So if you know LDMR, you know that we have to choose some finite group here and then generate that for the group, which can be readily expressed using the library. So again, with a variable statement, we can assume that G is some type which is finite, and is a commutative group structure on it, and we can say that G is some generator for the group, and then using the library, in the library we can prove the correctness and the security of this. We won't go into the security proof because it's more involved, but just to give a very basic example of how proofs look like. So when you work with Lean, you end up with things like this. So this is part of proving the correctness of the protocol. So this is the statement that you want to prove. And here is essentially the proof. And at any state you have a set of assumptions, of current assumptions in the proof, and something that you need to prove. And then you run a series of commands called tactics, which modify the goal and assumptions in some way. So here we replace the definition for decryption of LDMR with this definition, and you see that what you have to prove changed, and then we use lemma from the standard library to rewrite the code into something else. And we do this several times, insofar very manual. There are also quite strong at this point automation tools. For instance, this sub tactic here, which basically at this point, let's say that it magically closes the proof, but it does generate a proof in the type theory of the end, because it's a formal proof that is generated in the end. And later, for the security proof, one needs the assumption that the group one works in satisfies the so-called Zvi-Hellman decision of assumption, meaning that a triple G to the X, G to the Y, G to the Z, and G to the X, G to the Y, G to the X times Y can be seen with up to a bounding probability. Right? And this can be formalized in linear very similar to before, so we can again, using the distribution theory, pick some random numbers and define what it means that a distinguisher distinguishes indeed between the two with some probability up to some error epsilon, which we want to be very small in general. And then finally, in cryptolib, there is this main result, the semantic security for RMR, which states that given that the decision, the Diffie-Hellman assumption holds, then the semantic security for the protocol also holds, and I won't go into the proof. Okay, thank you.
So any questions? Thank you. This was a great talk. So I just wanted to ask if you know the status of it. Are you following up with this library? Because I'm trying to Google it and I found the example I gave, so but not the transition to. That's great.
No, so yeah, so the translation to Lean4 is something that I'm working on currently, but so it's not yet published yet.
Are there any words? Are there any more complicated protocols like I assume like for DNS or something like that, which have been verified in Lean or considered or something like that? Is it maybe something available for that?
As far as I know, no.
Yeah, because that would have been very interesting that the work we are doing at the various level, we could potentially like think about how we can do this applications like but yeah, this
also starts at kind of different category of languages, or how do you describe the difference?
So, yeah, to be fair, I'm not very familiar with F-star. In my understanding, F-star is more focused on, I would say, two differences. Mainly F-star is more focused on writing actual programs with proofs about them. So you wouldn't like formalize Fermat's theorem in F-star, for example. And also, maybe I'm wrong, but in my understanding, F-star doesn't really follow this small kernel paradigm with a small kernel that ensures soundness. So I think there is an SMT solver involved in F-star pre-verification, right? So so the trust base relative to the soundness is a bit more expensive in F-star kind of systems, as far as my understanding is. Maybe I'm wrong.
Just so tight for break. So
I think singling me out.
I really got it from delete it from the recording, so don't worry.